In the quantum numbers activity, we are studying the four quantum numbers. These quantum numbers came up in the analysis called the quantum mechanical model analysis that occurred in the early 1900s by several scientists. There was a big effort to understand the electronic structure, what the electron was doing in the atom and how they were distributed in the multi-electron atoms. That gave rise to the understanding that the wave nature of the electron is what needs to be studied. An equation called the Schrödinger equation was developed at this time by solving the Hamiltonian. Pretty complex math, physics, chemistry was involved. Within that Schrödinger equation, these four quantum numbers came out, and they are identified as N, L, and M sub L, and later this fourth one, M sub S, came out. And these are related to the energy, the locations of electrons, the actual electron within an atom. Here we have the four quantum numbers in this table. The first quantum number, called the principal quantum number, symbolized N, has to do with energy. And it can take on integer values 1, 2, 3, 4, and so forth. The smaller the value of N, the closer is that N level called shell to the nucleus. Think of a multi-electron atom. There's many shells. N equals 1 is the lowest energy shell. N equals 2 is the next one. N equals 3 is the next one, and so on. And N very much has to do with energy of the atom. The next quantum number, the angular momentum quantum number, symbolized L, has to do with, yes, angular momentum, and ultimately it has to do with shape. It also has to do with energy, as it turns out. L is restricted to the values 0, 1, 2, up to N equals 1. The magnetic quantum number, symbolized M sub L, that has to do with, we could say, orientation, yes. Also, it describes how many orbitals, how many little houses that can contain electrons there are within a certain L value. Going back to L for a moment, L is often referred to as the subshell. So N is the shell. So are we talking about a shell close to the nucleus, a small value of N, or a shell far from the nucleus, a large value of N? Within a shell, there are subshells, and those are having to do with L. A given subshell has so many orbitals within it, and that is where M sub L comes up. And those orbitals are locations where electrons can be found with a 90% probability. The restriction on the value of M sub L is M sub L can be negative L up to 0 up to positive L. So notice how there's a restriction or a limitation on these various quantum numbers. The last quantum number is called the spin quantum number, symbolized M sub S, and it has to do with whether we're drawing and picturing an electron with the spin up. That would be an arrow upwards. That would be M sub S equals positive 1/2. Or we draw the electron with an arrow down, and that would have the value M sub S equals negative 1/2. Okay, so these next paragraphs are more information about these quantum numbers. So the first one has to do with energy. The second one has to do with, for us, primarily shape. And It has to do with the shape of the orbital that it is describing, or orbitals, plural, it's describing. Alrighty, so L takes on values from, as we see in our limitation up here, 0 on up to n equals n minus 1. So when n is 1, L can only be 0. When n is 2, so we're a little farther from the nucleus, L can be 0 and L can also be 1. So there's two types of shapes within the shell n equals 2, and so on. Okay, so now we have the five different values L can take on that are shown here. It keeps going up from there. And we also have we can designate the value of L by a number, or we can designate the value of L by a letter. When L is 0, we call that an S type orbital. When L is 1, a p orbital. L is 2, d orbital. L is 3, f orbital, and so forth. The shape of all s orbitals is spherical. The shape of all d orbitals are what we call dumb shell. They have two lobes, a lobe above, a lobe below. Or if they're oriented on the x-axis, a lobe to the left, a lobe to the right. Or on the y-axis, a lobe behind and a lobe in front. When L is 2, we have those d orbitals, and they have bizarre shapes. They have more complex shapes. What we see in the picture is one of the possible d orbitals. And then the shapes just get more and more complicated as we go to larger values of L. In our next table, we're still pretty much working with L. So for n, when n is 1, so we're the closest to the nucleus in an atom, the allowed value of L is only 0. And we have just one orbital there. And we symbolize it 1s. So the 1 has to do with the value of n. The s is the letter character for L equals 0. When we are a little further from the nucleus in an atom, so we have n equals 2, well, L can be 0, L can be 1. When L is 0, we have a 2s atomic orbital. When L is 1, we have a 2p atomic orbital, where p is the letter symbol for L equals 1. When n is 3, we can have L equals 0, 1, or 2. So we have 3s orbitals there, 3p orbitals there, and 3d orbitals, where the d is the letter for L equals 2. And that just continues, where when n is 4, we're of course farther from the nucleus, we have L equals 0 for S, L equals 1 for P, L equals 2 for D, L equals 3 for F, F being the letter for L equals 3. The next quantum number, that magnetic quantum number, it is limited to values of negative L to 0 to positive L. So when L is 0, so we have an S atomic orbital, m sub L can only be 0. That means when we have an S atomic orbital, that subshell, we only have one atomic orbital there. When L is 1, we have the p atomic orbital, and L can go from -1, it can be -1 or 0 or +1. What that translates to is when we have the p subshell, there are 3 atomic orbitals there. So there are 3 places where electrons can be. When we have L equals 2, we have d atomic orbitals. They, for m sub L, can be -2 -1, 0, +1, or +2, that means we have 5 atomic orbitals in the d subshell. For F, L is 3, so m sub L goes from -3 to +3. That results in 7 atomic orbitals in that subshell. The last quantum number, a little easier, it just takes on 2 values. M sub S equals -1/2, that would be a downward arrow, or +1/2, that would be an upward arrow. The N, L, and M sub L, those describe the atomic orbital where the electron can be. M sub S describes the actual electron. Does it have a spin up or spin down? You can think of the 3 quantum numbers, N, L, and M sub L, kind of like as the address for that atomic orbital. And then M sub S is the electron, information about the electron in that atomic orbital. Does it have spin up? If so, upward arrow, +1/2 for M sub S, or does it have it spin down, and so forth. So we put this all together to have what we call energy level diagrams to work with. And here is an energy level diagram. So we have the energy going upward on the y-axis, and we have the lowest energy atomic orbital, the 1s atomic orbital, and then we go, that's the only atomic orbital in the n equals 1 shell. Then we go to the n equals 2 shell, and we have the 2s atomic orbital. A little higher in energy, we have the 2p atomic orbitals. Then we go to n equals 3, and we have a 3s atomic orbital, the 3p atomic orbitals, and the 5 3d atomic orbitals. When n is 4, we have a 4s atomic orbital, 3 4p atomic orbitals, 5 4d atomic orbitals, and 7 4f atomic orbitals. Now, what we're going to get into next is filling in electrons. So for a given atom, we'll have so many electrons. We fill in the energy level diagram, starting with putting electrons in the lowest energy atomic orbital and then working our way up to get through all those electrons. So we follow what's called the Aufbau principle. We populate the lowest energy ones first and work our way up. And when filling in the electrons, we have to think of several rules, principles. The first one is the Pauli exclusion principle, which ends up stating that we can put 2 electrons into an atomic orbital. One has spin up, the second one has spin down. We always start with spin up first. When we get to filling in electrons in the, for example, 2p atomic orbitals, notice that those 3 atomic orbitals have equal energy. The 2p atomic orbitals have a little bit higher energy than the 2s atomic orbitals, but those 3 2p atomic orbitals have equal energy. We say that they are degenerate. They have equal energy. So when we're putting electrons into the 2p atomic orbitals, we put an electron into the first atomic orbital with spin up. Then we don't put the second electron into that same atomic orbital with spin down. Rather, we go to the next atomic orbital and draw that next electron with spin up. So we always draw spin up first. We only draw a spin down if we're putting 2 electrons in the same orbital, but we spread them out when we have degenerate orbitals. That is Hund's rule. So let's see those practiced by looking at these sample energy level diagrams. So what we have is hydrogen, helium, boron, and carbon. For hydrogen, we have the energy level diagram, a partial energy level diagram shown below it. And for helium, it's shown below, boron below, carbon below. So orient yourself correctly. Okay, hydrogen has just one electron. So we put it in the lowest energy orbital, the 1s orbital. We draw it with spin up. So we've filled in the electrons for hydrogen with that. Now, the quantum numbers, the 4 quantum numbers for that electron in hydrogen are n equals 1, L equals 0, M sub L equals 0, and M sub S equals plus 1/2. So that's what the 1, 0, 0, 1/2 corresponds to. Helium, so we have the partial energy level diagram shown for it. Helium has 2 electrons, and we show those 2 electrons in the lowest energy atomic orbital. We draw the first electron with spin up, then the second electron with spin down. That's following the Pauli exclusion principle, that we can have 2 electrons in the same orbital, but they have to have opposite spins. What we would say about these 2 electrons in the same orbital with opposite spins is they are paired. They are paired electrons. Shift back over to hydrogen, it's 1s electron. That's an unpaired electron because it doesn't have another electron in that orbital with it. All right, so now going back to helium, the quantum numbers, the 4 quantum numbers for that last electron that we just drew, the one with spin down, the downward arrow, the quantum numbers are n equals 1, L equals 0, M sub L equals 0, and M sub S equal minus 1/2. Alrighty, so for boron, we have 5 electrons. So we put the first 2 in the 1s atomic orbital, they're paired. We put the next 2 in the 2s orbital, they're paired. And then we put that 5th electron in the 2p atomic orbital. In one of those, we draw it with spin up, put it in that first orbital. Okay, so now the quantum numbers for that 5th electron are n equals 2. We're in the second shell, n equals 2. L equals 1 because we're talking about a p atomic orbital, so L equals 1. M sub L is -1. Remember that M sub L can go from -1 to 0 to 1 for L equals 1. So we just choose that first value of M sub L, -1. And then we have the electrons shown upward. So we have M sub S equal plus 1/2. Carbon, we have one more electron. And so we put it into the next 2p atomic orbital. That's applying Hund's rule. That turns out to be lower energy, having those 2 unpaired electrons in different atomic orbitals than pairing them together in the same 2p atomic orbital. For that last electron, its 4 quantum numbers are n equals 2, L equals 1, M sub L is now 0, and M sub S plus 1/2 because we have spin up. So in comparing carbon and boron, we would say carbon has one more unpaired electron. Okay, so that's how we write the quantum numbers for electrons within the atom from the energy level diagram. What we have shown is giving the 4 quantum numbers for the last electron in the atom. So the 4 quantum numbers, they would apply to an atom. But we have what's called electron configuration, which is a summary of the energy level diagram that's easier to write. It's quicker to write than drawing the energy level diagram and putting all the electrons in. And that would be called the electron configuration. And it describes all of the electrons within the atom, not just one of the electrons. So what we list for that is the name of the atomic orbital, and as a superscript to the right of that atomic orbital, we list how many electrons are in that orbital. Okay, so for hydrogen, it's not shown here on this sheet. Hydrogen, its electron configuration would be 1s1. For helium, its electron configuration would be 1s2. For boron, its electron configuration would be 1s2, 2s2, 2p1. For carbon, its electron configuration would be 1s2, 2s2, 2p2. We have electrons that are kind of tucked within the atom and not very reactive. Those would be the electrons in lower shells, like boron. It has those two 1s electrons in the n=1 shell, and it has the 3 electrons in the n=2 shell. The 3 electrons in the outer shell are what we call valence electrons. They are the more reactive electrons. They're the ones that take part in the outside world. They take part in reactivity. So we would say boron has 2 core electrons and has 3 valence electrons. Carbon, its core electrons are the 2 1s electrons, so there's 2 of them, and the valence electrons are the ones in the n=2 shell, and there are 4 of them. So carbon has 4 valence electrons. Another way to write electron configuration is to recognize that the core electrons can be symbolized with a noble gas electron configuration. That is, helium has the electron configuration 1s2. So instead of writing the electron configuration for boron 1s2, 2s2, 2p1, we could write in square brackets He and then 2s2, 2p1, where the He would take care of the 1s2, the core electrons. So carbon's electron configuration we could write as helium 2s2, 2p2, and that would be shown here. Carbon, helium 2s2, 2p2. It's not saving a lot of writing when we're only in row 2 on the periodic table, but when we get down on the periodic table further where we have a lot of electrons, it turns out to save a lot of writing to go to the noble gas coming before that element and including electrons that are just after the noble gas in the electron configuration. Alrighty, so we come to the pre-activity, which look at if you want to. You don't submit it. It's got some good questions on it though. The report, so that one of course you'll turn in. So our first problem is to decide, given 3 quantum numbers, do they agree with each other limitation-wise? So review the rules again for what values n can take on, what values L can take on given a certain n, what values M sub L can take on given a certain L, and decide whether those 3, like A here, n=3, L=2, M sub L =3, whether those 3 are allowed together or if there's some violation in the limitations. Okay, so do the same for B and C. In number 2, we're giving the maximum number of electrons in an atom that can have these quantum numbers. So when n=4, there's a lot of different values that L can take on, and M sub L, M sub S. So I warn you that A is going to be a rather big number. You could use the energy level diagram and just count. So do that for A, B, C, and D, of course. And now we're then working with energy level diagrams. So what we're told to do is draw out the ground state condensed electron configuration. So that means using the noble gas notation. And then in the energy level diagram region, sketch the energy level diagram of just the valence electrons. So phosphorus, its valence electrons are going to be the 3s electrons and the 3p electrons. That's why we have just that partial energy level diagram shown. So you're going to put the electrons in, and then for this last part, the quantum numbers for the last electron. So of that last electron that you drew in the energy level diagram, give its value for N, for L, for M sub L, and M sub S. So do the same for silicon, for sulfur, magnesium. You may skip vanadium and iodine. Do them if you care to, otherwise you can skip them. I won't grade the vanadium and the iodine information, but definitely do number 4. So number 4 is considering the energy level diagram that you've drawn above. Answer these questions. So for phosphorus, you are deciding which is higher in energy, 3p or 3s orbitals, and answering the question whether the 3p orbitals are higher, lower, or equal in energy to the 3s orbital. And then still with phosphorus, are the 3p orbitals equal in energy to each other or not equal in energy to each other? And then you're now comparing phosphorus and silicon and deciding whether phosphorus has a higher number of unpaired electrons, a lower number, or an equal number of unpaired electrons. Remember, those are when we have just one electron in an orbital. That's called an unpaired electron, and that would be, because we draw spin up first, that would have an upward arrow. And in D, you're comparing silicon and sulfur. Silicon has a higher, a lower, or an equal number of paired electrons than sulfur. Okay, so paired electrons are when you have two together, one with spin up, one with spin down. They're together in an atomic orbital. Alrighty, so when you're done with this, scan it as a PDF file and submit it.